And today we have the joyful experience of hearing from Thomas More. Goes by Tom. He is presenting within the series that we've been doing, Responding to a Fractured World, Rethink, React, Recreate. And his particular title is The Exuberant Universe, Rethinking Creation in a Scientific Age. Now, let me tell you a little bit about Thomas. He's quite a remarkable man. He's a theoretical astrophysicist. I didn't do too well on that time. A theoretical astrophysicist, and he's the Reuben C. and Eleanor Winslow Professor of Mathematics and Natural Science at Pomona College. He's known as a very fine teacher. He has a fine reputation at Pomona. And one telling example of his teaching is when his grandson came to him and said, "Can you make lightning?" And Tom said, "Sure, I can." And they walked off to the library, to Tom's lab at Pomona and made lightning together. So this man really knows how to teach and be with people of all ages. Tom received his BS from Carleton College, working with Barbour and Joseph Sittler, who many of us have read and followed. And he did his PhD in theoretical physics from Yale University, where he also studied biblical Hebrew. So he is a man of many talents. In fact, he has lived both his public and domestic life in the worlds of philosophy, science, and religion. His father was a professor of philosophy and religion, and his mother and spouse, Joyce, are ordained pastors of the United Church of Christ. Tom himself studies questions on the boundary between philosophy and physics, and he teaches courses in general relativity and particle physics, as well as science and religion. His publications include 2 textbooks, 6 Ideas That Shaped Physics, and a General Relativity workbook. So you have a sense of the span of Tom's work. Most of all, Tom is a wonderful human being, very wise, and with very much to teach us today. Thank you for being here, Tom, so much. It's all yours.
Okay. I'm very happy and honored to be here. And I really want to thank you, Mary Elizabeth, for inviting me and for such a kind introduction, and for all of you for coming to listen. I really appreciate it. And I hope I can live up to Mary Elizabeth's wonderful introduction. So, and to that end, I'm going to warn you that this talk has 2 parts. In the first half, I'm going to try to explain some of the scientific reasoning behind what I mean by an exuberant universe. And while I've tried to target these explanations to someone with roughly a high school background in physics and chemistry, I recognize that some of you may find it tough going. Please bear with me. The second half will be much more accessible. So, and I'm going to try and share my PowerPoint presentation here. Let's see if this works here. I hope you all see that. I want to begin by talking about in 1802, theologian William Paley published a book entitled Natural Theology, or Evidences of the Existence and Attributes of the Deity. In it, Paley famously argued that if one encountered a pocket watch dropped on the heath, one might reasonably conclude from its intricate mechanisms that it was a created object designed by an intelligent watchmaker instead of being shaped by random physical processes the way a nearby rock might be. In a similar way, he argued, the intricate biological mechanisms evident in even the simplest organisms implied the existence of an intelligent creator. This influential line of reasoning was subsequently demolished by Charles Darwin and his successors, who showed that evolution through natural selection provided the means to construct intricate organisms from random processes. Research has documented how even structures like eyes and wings, whose many parts must work together in complicated ways to function at all, can evolve from simpler structures that originally had different purposes. Now, Paley's argument is commonly remembered as being an example of the naivety of this kind of religious thinking in a modern age, and the whole concept of natural theology has fallen into disrepute. Ironically, though, science had demolished one argument for a creator, and recent scientific discoveries have made what seems to be an even stronger argument for that idea. In recent decades, our understanding of the cosmos has become sufficiently complete, and one can reasonably answer the question of what the universe would be like if we changed this or that aspect of physics. The result has surprised everyone. It turns out that making even relatively tiny adjustments to those aspects almost invariably leads to universes not only incapable of supporting life, but virtually any kind of complexity. The universe seems fine-tuned for complexity. For us to really understand the full force of this statement, I need to step back to provide some background. The twin pedestals on which modern physics rests are Einstein's theory of general relativity and the theory that physicists call the standard model of particle physics. Taken together, these two theories describe all known physical phenomena, but the equations in these theories that describe the laws of physics involve a set of numerical quantities physicists call physical constants, whose values are not determined by those laws. For example, the core equation of general relativity I've displayed on the screen there. The T in brackets is a mathematical object describing a blob of matter and energy, and the capital G in brackets describes the gravitational field created by that blob. These quantities are variables in this equation. One could apply the equation to different blobs of matter and energy, for example, a planet or a star or a galaxy, and calculate the unique gravitational field created by that particular blob. However, the K in this equation is a universal constant. It specifies how strong the gravitational field created by a given blob will be. The equation, and thus the physical law that the equation describes, does not determine what the value must be. We must measure K experimentally to determine its value. The law, the equation, works no matter what value of K we find, but in our universe, K has a particular value that applies everywhere and for all time. This is what I mean by a physical constant. Other examples include numbers that characterize the strengths of the three other fundamental ways that particles can interact, the masses of the various elementary particles, the electric charge of the electron, the rate at which the universe is expanding, the number of spatial dimensions, and so on. How many such constants exist depends a bit on how one chooses to count them, but to choose a round number, there are roughly 40 independent physical constants that appear in the fundamental equations of physics. What we have recently come to understand is that the characteristics of the universe depend critically on the relationships between these numbers. For example, consider the relationship between the constant determining the strength of the attractive force between two protons, which physicists call the strong nuclear force, and the constant determining the strength of their electrostatic repulsion. You might recall from high school chemistry that different chemical elements have different number of protons in their atomic nuclei. Hydrogen has 1 proton, helium has 2, lithium has 3, and so on. So forming the chemical elements requires protons to be able to stick together even though they repel each other because they all have the same electric charge. If this attractive force is too weak, protons won't bind together, and we have no chemical elements. If the attractive force is too strong, then protons glom onto each other at the beginning of the universe, and we have no hydrogen left, which is necessary for fuel for stars to exist. If both forces are very strong, all atoms become radioactive and no stable molecules exist. The following chart shows the possibilities for just the relationship between these two physical constants. So you can see in this chart, hydrogen can't form in this range. Chemical reactions are impossible because all atoms are radioactive in this range. Heavier elements cannot exist. Stars can't shine in this range. Carbon-based life is possible in this thin area marked in red. And we are here in that set of relationships. Now, the strength of the gravitational interaction relative to the size of atoms is also important. If we make gravity stronger, stars would form more easily, would burn hot and die quickly. Galaxies would be smaller and more crowded, and frequent near collisions between stars would make stable solar systems impossible. But you make gravity weaker, and stars and galaxies won't have enough time before the expansion of the universe makes the primordial gas too thin for star formation to take place at all. I often teach a course in upper-level particle physics, which contains many arcane features whose only explanation is our existence. Why, for example, are there 3 families of fundamental particles when we only need 1 to explain all the matter in our universe? It turns out that for subtle mathematical reasons, if we had fewer than 3 families, there would be no distinction between matter and antimatter. So matter and antimatter would be created equally by the Big Bang and subsequently completely annihilate, so that the universe would consist only of photons. Why does the Higgs particle exist? Yeah, I think you've probably heard relatively recent news about the Higgs particle. Well, if it didn't, all particles would move at the speed of light, making chemical structures impossible. Let me give one final example. Ironically, this argument was first posed by none other than William Paley, but is not as well known as his watchmaker argument, and I think perhaps precisely because it was not so easy to refute. One of Newton's basic laws that you maybe learned in high school is that the force of gravity between 2 objects varies in proportion to 1 divided by the square of the distance between those objects. By Paley's time, mathematicians had shown that if that dependence were any other function of distance, stable planetary orbits would not exist. We now know that this particular dependence is linked to the number of spatial dimensions that exist. So we must exist in a 3-dimensional universe for gravity to be dependent on inverse square of the distance, which in turn allows for stable planetary orbits to exist. Here, I'm going to show another graph that shows the possibilities considering the number of possible space dimensions that a universe might have versus the number of time dimensions. And you can see that everywhere except where we are, 3 space dimensions and 1 time dimension yields universes incapable of supporting complexity. for various reasons. So I could go on and on about this. My overwhelming sense as a theoretical physicist is that the complexity of the universe is like a beautiful artistic edifice delicately poised on 40 pillars. You change the length of any one of those pillars, and the entire structure collapses to rubble. The statement that the universe seems fine-tuned for complexity is, for historical reasons, called the anthropic principle, and maybe you've heard about it in that language. I think that this is an unfortunate misnomer, as it incorrectly focuses our attention on whether the universe is constructed so we, as humans, exist. The issue in my mind is much more about whether any kind of complexity can exist. So so this concludes the science part of the talk. And the main lesson that I hope you'll come away with is that the universe seems to be extraordinarily fine-tuned for any kind of complexity to exist. Like Paley's watch, that complexity begs for an explanation. So what kind of conclusions can we draw from these scientific facts? We have basically 5 choices. One is the universe was created to support life. The second is that our vision of complexity is too anthropocentric. Life might exist in other forms than we can easily imagine. The third is that a future complete theory of physics might exist that would constrain all of those 40 constants to the values we observe. So it's all in the physics somewhere. Fourth is that our universe is just one of many, one that happens to support life. The fifth option is that we just may be amazingly, incredibly lucky. I want to clearly state before we go much further that we cannot take the fine-tuning of the universe as any kind of proof of an intelligent designer. The other 4 conclusions on this list are genuine possibilities. But I'm going to argue that all 5 of the possible conclusions are metaphysical conclusions based on one's personal beliefs about how the universe is ordered, rather than on any kind of science. Science depends on posing hypotheses that can be experimentally tested and potentially rejected. None of these inferences can be tested, even in principle. Let's look at each one of these claims in turn. I think all of us here, both theists and non-theists, are familiar with the dangers of the concept of an intelligent designer. There are logical and ethical problems with reconciling the omnipotent and wholly loving God of traditional theism with a designer who would create a universe where the natural existence of most creatures is nasty, brutish, and short, as Thomas Hobbes put it. A conception of a designed universe can also lead to complacency about the injustices implicit in whatever the current social order might be because, quote, that's the way God created things to be, unquote. I personally think that only the kind of God envisioned by process theology is consistent with the first conclusion, and I'm going to talk more about that later. But the main problem for scientists with this conclusion is that it cuts off any further scientific advancement. Once you answer a question with, because God made it that way, then further scientific research into that question becomes irrelevant. Some other conclusions at least allow for further scientific investigation. The idea that we are simply too anthropocentric is the knee-jerk reaction of most of my students when confronting this issue. The strength of this conclusion is that at one level it's almost certainly true. Our imagination for the possibilities is surely limited. But when we push this harder, its plausibility as a sufficient explanation becomes harder to defend. consider the tiny sliver of possibilities, this little red space between the two constants in the first figure that I displayed, complexity only exists in a tiny sliver of this diagram. When we consider that we have 40 such constants and the relationship between all need to be tuned correctly, the probability of creating our kind of universe seems vanishingly small, even if it is impossible to estimate precisely. If the probability of a universe being consistent with our form of life is sufficiently small, say to take a number 1 in a trillion, then even if there are 1 million more possibilities for forming complexity or life than we can imagine, the probability that the universe could support any kind of life is still only 1 in 1,000. So that explanation therefore runs into trouble. A hypothetical future physical theory that requires our 40 numbers to have the values they do for logical or mathematical reasons is certainly possible. And the history of physics offers some examples where theoretical advances have led to reducing the number of truly independent physical constants. Moreover, this conclusion certainly motivates some future research. But no one has yet developed such a theory, and until someone does, we cannot be certain that such a theory exists. The fourth conclusion, postulating a multiverse, is the most popular explanation among scientists who are uncomfortable with any kind of theistic explanation. Certainly, if untold myriads of universes exist, then having at least one universe compatible with life becomes more probable. And it's no accident then that we are living in such a universe. Moreover, certain physical theories describing the earliest moments of the Big Bang are consistent with forming such multiverses, maybe even an infinite number. It provides many opportunities for further scientific research. But some scientists are still uncomfortable with this solution. Multiplying an already unimaginably immense universe by infinity just to solve a puzzle seems like an extravagant violation of the principle that the most likely solution is the one with the fewest elements. Poor William of Ockham would be spinning in his grave. Moreover, it logically just pushes the problem one level deeper. Well, why do the laws of physics that allow for multiple universes to exist happen to be the laws and not some other laws that don't? The best version of this multiverse approach that I know of applies the theory of natural selection to universes. Instead of having an infinite set of simultaneously existing universes, perhaps we have just one universe, but it oscillates. It undergoes a big bang, it expands, and then collapses back to a point and repeats the cycle, each time with some readjustment to the physical constants. This is not totally incredible, because the theory of general relativity does allow for such an oscillating universe. Moreover, suppose that there was some kind of physical influence between one cycle and the next that would favor pushing the constants towards a more complex universe. Our universe then becomes the result of many such cycles, evolved to the point where it can support the kind of complexity that we require. Instead of many universes in space, we have many universes in time. But clever as this solution is, it still has problems. While general relativity does allow for an oscillating universe, it does not provide any mechanism for even adjusting the physical constants randomly, much less pushing them towards values that support complexity. Even if such a mechanism exists, again, the solution just pushes the question up one level. Who set up these laws in such a way to favor complex universes? The fifth conclusion, that we are just lucky, I should go back to the list there. So I've talked about four here, that our universe is just one of many, whether that's in space or time. And I'm talking now about the fifth. Fifth conclusion that we're just lucky is even less of an explanation than the first. It might be true, but it ends all discussion. The universe is simply meaningless. So I want to emphasize and re-emphasize that none of these conclusions is any more scientific than the others. Don't let anyone sell you the line that multiverses are a proven or even a provable physical theory. The particular laws of physics to which people appeal to support either version of the multiverse hypothesis are speculation, first of all, and they imply that even if they were true, we cannot test that hypothesis, even in principle, because the other universes are either too far away in space or time to be observed. If one favors any one of these hypotheses over the other, one does it for reasons based on one's personal sense of how the universe works, not for scientific reasons. I believe it to be no accident that most of those strenuously claiming that the multiverse is scientific are self-declared atheists devoted to what I would call the religious idea that science can explain everything. I also think they've not fully faced the issue that even if their theory is true, it does not ultimately answer the question of fine-tuning, but simply pushes it one step further away. I personally very much in favor of further scientific investigation of the middle three conclusions. At least they do not preclude scientific exploration, and maybe we'll learn something useful. But in the remainder of the talk, I want to suggest a different way of thinking about all of these approaches. When I teach my students about worldviews people held in the first century, and particularly the concept of angels and demons, their knee-jerk reactions reject such ideas outright as superstitious nonsense. They think that the concept of a sick person being possessed by a demon is particularly ridiculous. But I say to them, well, when I catch a virus, the virus's set of instructions, its genetic material, has entered my body and has commandeered my body's machinery for purposes of its own, purposes that are destructive to me and make me do things I don't want to do, like sleep all day. Demonic possession sounds like a pretty accurate description of what is happening to me if one lacks the means to understand the mechanism. I then ask them, does Pomona College have a spirit? That is, does the collective set of relationships between professors and students and staff and alumni over historical time have an emergent character that is unique to the college and has a life that transcends the individuals involved at any one time? Well, yes, they would say. We call that Pomona's culture. But I challenge them. Isn't that just different language for describing the same thing? Why not call that Pomona College's angel, to use John of Patmos's language in the first chapters of Revelation? Moreover, is it possible that aspects of the college's spirit might work towards good or evil outcomes, making it angelic or demonic, independent of and maybe in spite of the intentions of its participants? So I challenge them to think, is it possible that the ancient thinkers had a language for talking about this real, emergent, but immaterial, that is relational, aspect of bodies and institutions for which we now only have poor translations that blind us to certain things that we might see more clearly? If your language, like classical Hebrew, lacks a word for blue, how do you describe the concept of what that English language color means to someone speaking that language? With this in mind, I now pose to you all this question: what is the spirit of our universe? Especially considering the alternatives clarified by modern science, and for whatever reason, it doesn't matter why, our universe is fine-tuned for complexity, for life, for consciousness, for abundance. This is our universe. And I'm pausing on this last picture to note that except for the single star that appears up in the corner here, every dot up in this whole picture is a galaxy as big as our galaxy. We estimate that the universe probably contains 500 billion galaxies, each of which contains probably roughly 200 billion stars. The universe is immense. Ours is an exuberant universe. Be fruitful and multiply, it tells us in 1,000 different ways. The spirit of our universe also has an evident history of pushing from simplicity to complexity. Gas evolves to galaxies, and stars that create all the chemical elements beyond hydrogen and helium. Supernova push the newly forged elements into space, where they form new stars, now with planets, literally made of stardust. And on a few of these planets, chemical processes become self-perpetuating, and organisms begin to evolve, creating larger organisms from networks of smaller organisms, ever pushing towards complexity. In us, on a particular pale blue planet, orbiting a medium-sized star in the suburbs of an ordinary galaxy, the universe has entered a new phase. We are the first organisms we know of, though probably not the only ones, to transcend the bounds of the slow evolutionary processes that created us, to create through language, culture, and consciousness a richer and more complex set of relationships that can evolve much faster and more dynamically than pure biological evolution. The spirit of the universe flows through us, pushing us forward to new levels of consciousness and interrelatedness. This is a story of evolving relationships from the subatomic to the cosmic that I think process theology captures especially well. The God of process theology is not simply a cosmic watchmaker, but an active participant in the universe's evolution and is shaped by that evolution. The spirit of the universe that expresses and embraces the totality of the relationships that form the fabric of our universe. If the spirit of the universe itself is pushing us towards greater abundance, complexity, and consciousness, it makes sense that we fit best in that universe if we work towards the same ends, that is, working for God's dream for what the universe might become. This has certain ethical implications regarding how we treat each other, the other organisms of on our planet, and the planet itself. I think that some of the authors of the Bible had an inkling of this, even without the advantages that science has given us, their distant descendants. I teach my students that the first chapter of Genesis is not about the cosmos, since the author's cosmology is no different than the standard Mesopotamian cosmology of the time, but rather a point-by-point deconstruction of the Babylonian creation myth, written by people shaped by captivity in Babylon. It was therefore primarily a political document. Nonetheless, I do think that, as I alluded above, it does capture that same life-affirming spirit of abundance that I see written into the cosmos itself. But perhaps the ancient author who understood this best was actually the author of the book of Job. Beset by unexpected tragedies, our brother Job spends almost his entire book complaining to his friends about God's injustice. As the book progresses, his universe narrows to a courtroom and his image of God to that of an unjust judge. Though he is a lot closer to God than his friends, he needs a serious attitude adjustment. When God finally speaks to Job from the storm, it seems that God offers no answer to Job's complaint, but rather more oppression. Here's a translation of Job 38, verses 1 through 7, taken mostly from Robert Alter's translation. The Lord answered Job from the storm and said, "Who is this darkening counsel in words without knowledge? Gird up your loins like a man. I'll ask you that you may inform me." Literally, you may make me know. "Where were you when I founded the earth? Tell if you know understanding. Who set its measures, do you know? Who stretched the line upon it? In what were its bases sunk? Or who laid its cornerstone? When the morning stars sang together and all God's children shouted for joy." These seemingly rhetorical questions pound at Job, emphasizing his smallness and inadequacy. And indeed, Job initially takes this as more abuse, at first responding to God only sullenly. But as commentators J. Gerald Jansen and Robert Alter argue, God's purpose is different. God does not offer a simplistic answer to a simplistic question, but rather seeks to unfold before Job a much larger picture of God and God's universe than either Job or his friends have imagined. Within the frame of the universe as understood in the 4th century BCE, the poet behind Job constructs an astonishingly rich picture of God's creation, a vast world that utterly transcends the human realm and is yet beholden to God. Nature writing in that time period tended to emphasize either nature's pastoral calm or violent dangers. But the poet here presents a uniquely unsentimental vision that emphasizes nature's wonderful strangeness, where merely human categories of justice become meaningless. In the process, God calls Job as a human, unique among God's creatures, to a new and larger vocation, to be an observer and appreciator of these wonders, and to become larger as a result. Ironically, God really wants Job to know who set the universe's measures, to be able to answer, "Yes, I do know," to God's rhetorical questions. God wants Job to live to his calling, to be a creation becoming aware of itself. Job's final response shows that maybe he's starting to get it. He says, "I've uttered what I did not understand, things too wonderful for me, which I did not know. I dissolved and changed my mind regarding dust and ashes." Here, I follow Jansen's translation. The Hebrew verb ma'as as not. The NRSV is to despise myself. The Hebrew lacks myself, and despise alone doesn't make sense, but rather according to its attested alternative meaning of dissolve. Jansen also argues that dust and ashes refers not to the mourning process, but to humans as formed from dust. God calls Job and us as dust to both self-awareness and awareness of God. And Job responds. He now sees who he is in a different light. My Hebrew teacher also taught me that the verb yada, to know, the root of the word da'at, knowledge, and many other words in God's speech, mean to know something through experience. Now, we might take science to be the epitome of its opposite, abstract knowledge, but this would be a mistake. The whole point of science is to learn by experience. That is, by experiment and by testing hypotheses, which grounds knowledge in reality instead of speculation. Of course, most people learn science secondhand, but I can attest that the fortunate scientist over decades develops a deep da'at grounded in genuine experience and mastery. Through such people, we can all participate in the call to be knowers of the spirit of our universe. So perhaps the journey through all these questions can help us embrace the fullness and strangeness of our exuberant universe, to allow that da'at to shape our spiritual sense of ourselves and our part in the spirit of the universe, so that we are not trapped in small mental prisons, but rather are liberated to participate in the universe's ever-enfolding exuberance. Maybe we can learn to celebrate with gratitude the miracle of simply being alive on a beautiful planet in an incredibly beautiful and complex universe, a universe that did not have to be this way. Merely being alive to see this is an incredible gift. A gift, by the way, that took 13.74 billion years to deliver. As the living dust of the morning stars who sang together long ago, let all the children of God shout with joy. Thank you very much for listening.
Tom, thank you so very much. This was extraordinary. Your knowledge and your ways of weaving together the various fields that you've studied is incredible. Thank you so much.
My pleasure. Thank you.